Hi, this is Sai Pothana, founder at Embedded Systems AI LLC. In this video, we are going to explore the DOCSIS 4.0 physical layer architecture, the next generation broadband PHY framework defined by Cable Labs for ultra-high capacity hybrid fiber coax networks. This specification extends the DOCSIS 3.1 OFDM foundation and introduces full duplex DOCSIS, extended spectrum DOCSIS, higher upstream capacity, lower latency, advanced OFDMA operation, and scalable distributed CMTS architecture. The goal is to transform existing cable infrastructure into a future-ready multi-gigabit platform while maintaining backward compatibility with DOCSIS 3.1 and earlier systems. The architecture separates control plane, data plane, management plane, and RF-PHY functionality. The DOCSIS code communicates through Ethernet and IP transport networks with remote PHY devices, also known as RPDs, deployed closer to subscribers in the HFC network. This distributed model reduces analog optical transport complexity, RF impairments, latency, and scalability bottlenecks. So architecture supports remote PHY, remote MAC PHY, timing synchronization, and precise clock distribution. There are two major DOCSIS 4.0 operating models, FDX OFDM, FDD OFDM. FDD, frequency division duplex, separates upstream and downstream spectrum into dedicated frequency bands. FDX, full duplex DOCSIS. It allows simultaneous upstream and downstream transmission over the same spectrum. To accomplish this, DOCSIS 4.0 introduces echo cancellation, interference mitigation, sounding procedures, adaptive equalization, and advanced OFDMA scheduling. The PHY sublayer also integrates LDPC and BCH FEC, OFDMA modulation, interleaving, pilot insertion, burst processing, and dynamic spectrum allocation. These mechanisms together create higher spectral efficiency, lower latency, and significantly greater upstream capacity. In FDD operation, upstream and downstream occupy separate spectrum regions. Guard bands isolate the directions. This resembles traditional DOCSIS operation. DOCSIS 4.0 extends FDD operation up to 684 MHz upstream and as high as 1764 MHz downstream. This mode is known as ultra-high split or UHS. In contrast, FDX operation uses shared spectrum. The same frequencies carry upstream OFDMA and downstream OFDMA simultaneously. This dramatically improves spectral efficiency and enables near-symmetrical multi-gigabit services. However, simultaneous transmission introduces self-interference, adjacent channel interference, echo propagation, and reflection management challenges. That is why DOCSIS 4.0 introduces sophisticated PHY algorithms for echo cancellation, channel sounding, adaptive filtering, and interference estimation. On the downstream transmit path, MAC frames enter the PHY, packets are formatted, forward error correction is applied, interleaving improves robustness, QAM mapping assigns constellation symbols, and the IFFT generates OFDM symbols. A cyclic prefix is then added to reduce multipath interference. The signal is then upconverted, amplified, and then transmitted into the HFC plant. On the upstream receive path, the RF signal is digitized, synchronized, transformed through FFT, and then equalized, demapped, deinterleaved, and then FEC decoded. The PHY module continuously performs modulation error ratio estimation, automatic gain control, phase noise compensation, timing synchronization, and link adaptation. The PHY processing is heavily optimized for large OFDMA bandwidths, low latency, and dynamic channel conditions. Echo cancellation in FDX is one of the most important innovations in DOCSIS 4.0 because FDX transmits upstream and downstream simultaneously over the same frequencies. The receiver hears its own transmitted signal. Without correction, this self-interference would overwhelm the receiver. DOCSIS 4.0 therefore introduces adaptive echo cancellers, channel sounding, interference estimation, and dynamic calibration. The PHY continuously measures reflection paths, cable plant changes, insertion loss, and interference signatures. The echo canceller builds a mathematical model of the local transmission path and subtracts the locally generated interference from the received signal. This enables stable, simultaneous, bidirectional communication across the same spectrum. Traditional DOCSIS systems used limited upstream spectrum and heavily relied on asymmetric services. DOCSIS 4.0 expands usable spectrum dramatically. FDD operation can extend downstream frequencies toward 1.8 GHz. FDX introduces configurable full duplex allocated spectrum regions with multiple deployment models. In the classic FDX model, the upstream and downstream frequency range is fixed and shared. And in scalable FDX model, the upstream and downstream frequency range is configurable and shared. And in unified model, the frequency spectrum for upstream and downstream could be used in FDD or FDX modes. The specification defines configurable spectrum allocations for 96 MHz, 192 MHz, 288 MHz, 384 MHz, and 576 MHz FDX operation. This flexibility allows operators to optimize deployments based on amplifier cascades, plant quality, subscriber density, and coexistence requirements. The cable modem contains OFDM receivers, OFDMA transmitters, FFT, IFFT engines, adaptive equalizers, LDPC decoders, timing recovery, and dynamic power control systems. The modem supports ranging, channel sounding, synchronization, adaptive modulation, and PHY telemetry reporting. DOCSIS 4.0 cable modems are substantially more sophisticated than earlier generations because they must dynamically adapt to varying spectrum allocations, FDX coexistence, low latency requirements, and real-time interference conditions. The modem continuously exchanges PHY intelligence with the CMTS to optimize performance. DOCSIS 4.0 physical layer technology represents one of the most advanced broadband PHY systems ever deployed over coaxial infrastructure. By combining OFDM and OFDMA, full duplex communication, extended spectrum operation, advanced error correction, echo cancellation, and distributed CMTS architecture, DOCSIS 4.0 enables cable operators to deliver multi-gigabit symmetrical broadband, ultra-low latency, and scalable future-ready services, all while leveraging the enormous installed base of HFC networks worldwide.